What are you trying to do?
I'm trying to find a way. So we have this whiteboard thing that's really nice. I'm trying to find a way to make it so that you guys can draw on it as well. So try drawing on it really quickly, actually, and then let me know.
Nothing.
No?
Do you have to record these?
I don't have to. Do you not want me to?
I mean, I would prefer not, but it's no big deal.
Because I was thinking I could like post them. I think they will have to be recorded by my boss or something like that. But I was thinking I could post them in Open Campus or something like that. Does that change your mind or no?
Huh?
Does that change your mind or no? Because I could just turn it off if you want.
It doesn't matter.
Dang, I really wanted to draw or have you guys draw on this.
Is there a button where you like get the pen or something?
I think it's on settings where you can let participants draw on your screen too. Wait, am I still on mute? No, I'm not.
No, you're not. Huh.
Why does it matter?
Yeah. Why is it there?
That's how it bonds onto the diene.
She said that's how it bonds onto the diene. Kind of. It helps out with it in a certain way, right?
Does that have to do with stereochemistry?
Not quite. It has to do more with. It actually has more to do with regiochemistry.
Mm-hmm. Oh, okay.
So if we have an electron withdrawing group next to anything, what does it mean for an electron withdrawing group to be there? If we think of something like a leaving group, what does that leaving group make the carbon that it's on?
That like
I'll give you a hint. It's one of these.
an electrophilic?
Yeah. So it makes it an electrophile. Anything else?
No.
I think that's pretty much all the big important parts. So I guess I'll just draw the mechanism because the mechanism is the same every single time. There's nothing really special about it. But there's a lot to talk about.
Alex, sorry, could you explain how it being an electrophilic carbon is related to the part on the diene?
Yeah, we'll talk about that in a second.
Okay, thanks.
So your question was on the diene or the dienophile?
Just like how they're related, how the electrophilic carbon and what that communicates with the diene.
All right. So I'm gonna erase this stuff. Oh no! Dang it. Dang it. I guess I have to leave that crappy arrow there. So does anyone want to jump in on that conversation before I kind of like do an explanation?
Nope.
No. Moses, do you have anything to say?
What was it about again?
So her question was, why does the electrophilic nature of the dienophile and the nucleophilic and electrophilic nature of the diene matter? Was that pretty much your question, right, Alex?
Yeah, like how they're related, like what it looks like.
Yeah.
I mean, with the mechanism, I know it's all one step, and I know it kind of involves the dienophile attacking the diene, but the diene also ends up attacking the dienophile in one of its carbons as well, I believe.
So basically the electrophilic carbon, the nucleophilic carbon, or the electrophilic carbon on the dienophile, and then the nucleophilic and electrophilic carbons on the diene will kind of determine the regiochemistry of a product. So it basically means where are things going to end up connecting, what attacks what, and where moves where. So if we look at, I guess while I'm drawing this, what's the definition of a nucleophile or an electrophile?
An electrophile seeks electrons.
Yeah, so an electrophile seeks electrons. That's good. And then what about a nucleophile?
Donates.
It's electron rich.
Yeah, so it's electron rich versus electron poor. So what's the typical trend when it comes to when a nucleophile is in the presence of an electrophile? Like if we have a mechanism.
Well, doesn't the nucleophile just attack the electrophilic carbon?
Yeah, exactly. Nucleophiles like to attack electrophiles, and electrophiles like to be attacked by nucleophiles. They have something to offer one another. So I'm going to look at this example really quick, and we'll be able to kind of like say where the electrophilic and nucleophilic carbons are in this problem. I'm actually going to make this make that this guy. So in terms of observing which one is the electrophilic, which one is the electrophile on the dienophile, what do we have to do?
Which one is the electrophilic?
Yeah, so it's either going to be this one or this one. But we have to determine that. So what do we do?
Mm-hmm.
Just look at the reds.
Yeah. Finish your sentence.
Just look at the resonance structures and see where the charges end up, or delocalized, I mean.
Yeah, exactly. So the reason why these withdrawing groups are there, I mean, they could be pretty much anything that has that contributes to resonance, or it could be something that is just really electronegative, right? So technically, a withdrawing group can be like a bromine or a chlorine or something like that. But more commonly, they're going to be something with resonance. So what we have to do is we basically have to just say, okay, well, let's just draw a resonance structure for this guy. And this will help us determine so if we draw this resonance structure, is it complete yet?
No.
Yeah, so Moses says no. What else? What do you guys say?
No.
The bottom carbon is going to be positive.
But yeah, that's good. So the bottom guy is going to be positive. So if this guy is positive, Maddie and Sarah, do you mind if I unmute you?
Okay.
Okay. All right. I want everyone to get involved because otherwise it's just going to be some people kind of like taking notes and not getting. I mean, it's an important time to be able to talk about this stuff rather than just observe. So if this guy has a positive charge, is it going to be an electrophile or a nucleophile?
I don't know.
So I guess really quick,
It's a nucleophile?
say it's a nucleophile. Well, think, so if it's a positive charge, does it want electrons or another positive charge?
It wants
It wants what?
electrons.
Yeah, it wants
So
electrons.
it's an electrophile.
Yeah, so it's an electrophile. When we think of the word electrophilic, think of it, I don't know an appropriate term to compare it to because everything else is like kind of, everything else with a file in it is kind of inappropriate. So I'm not going to mention them. But the file just means that it wants that, it likes it. So if this guy is the electrophile, then if we look at the mechanism back over here, is it going to be this carbon? I'll call it carbon 1. Or is it going to be this carbon, carbon 2? Oh, wait, just 1 second. That was a stupid question. Oh, wait, no, that wasn't a stupid question. So I guess the question is it going to be the one that is being attacked, or is that going to be the one that's going to be donating?
The electrophiles getting attacked.
Okay, so Alex, you say that it's attacked. And then what about the rest of you? What else do you guys say?
What was the question?
So, so if this carbon down here is an electrophile, then if we look at the mechanism over here, back in this corner, is it going to be this carbon or this carbon? Is it going to be the one that's being attacked, or is it going to be the one that's attacking?
That's an electrophile?
Yeah, so it's an electrophile.
Oh, okay, I see what you're asking.
Yeah.
Be attacked.
So I have 2 people saying it's going to be attacked. And I see Moses holding his breath.
No, it'll be attacked.
Yeah, so Moses agrees. So, all right. So yeah, you guys are right. So it's going to be attacked because as an electrophile, it wants to have electrons. Electrons are always going to be going towards that guy. So electrons attack electrophiles. So that's basically how you want to analyze these things, is you want to do resonance structures and you want to see where does the charge end up? Does it end up on the carbon, or I guess what carbon does it end up on this alkene? So I'm going to erase some stuff really quick. Do you guys mind if we go, oh, dang it. Do you guys mind if we go overtime, by the way? Or do you guys have like places to be and people to see? I hope not.
We're quarantined. Where are we gonna go?
Where
Yeah.
are we gonna go?
To the kitchen, to the garage.
I have my Starbucks. I'm fine.
All right. Dang it. Okay. So in this case, we know that this guy is going to be attacked. And so if that's going to be attacked, then we just have to figure out which one is going to do the attacking, right? On this guy.
Yeah.
So how do we figure that out? Or does that question make sense?
Resonance?
Yeah.
Yeah, just more resonance. The Diels Alder reaction has a lot to do with resonance. So, so where do we want to start with this resonance structure on the diene?
The bottom pi bond.
Just saying right here. So where do you want to move that?
To the
Low bond?
yeah.
So you want to move that right here?
And then the top pi bond goes up to the O, like the bond attached to it.
Just saying like that.
Yeah.
So the product of that is going to be
That looks weird.
No.
so what's wrong with this?
Too many.
What
Too
was
many
that?
electrons. It has too many. It's over the octet rule.
Yeah, so it's, I'm just going to call it electron fat. Except I put an H, so it's electron fa. So yeah, so that doesn't work. But you're thinking the right idea. And it's always good to try, so I applaud you. So what's another resonance structure that we could look at?
I mean the alkoxy is electron donating, so we can always donate electrons moving down.
So you're saying like this?
Mhm.
Yeah, and then the pi bond just moved down.
Yeah. So everything just kind of moves like that. It's just a waterfall of electrons. I think it's a very pretty image. Waterfall of electrons. So that makes, so these electrons from this guy jump to this carbon and it makes a negative charge. So what does this tell us? And is everyone following pretty well?
Yeah.
Okay, good.
But it's a nucleophile?
So what is a nucleophile?
Mm,
The part with the negative charge,
bottom
right?
carbon?
Yeah.
Yeah, so this is a nucleophile. So now this tells us how everything is going to connect, right? So it tells us basically what arrow is going to go where. I'm going to draw this back. So it tells us which one is this one, which one is this one, and which one is this one. So I'm going to move over here now. I'm going to redraw it. I mean, the way that I would recommend kind of studying this is just going through this process for every problem in the book that you can find that has Diels Alder problems. But then on the exam, hopefully all that practice will go to a point where you just can kind of say, oh, hey, this one is going to be the electrophilic carbon, or this one is going to be the nucleophilic carbon, or something like that. So hopefully you'll get to a point where you can just kind of see it, but it takes some time. So so we know that this one's going to be electrophilic, and this one is going to be nucleophilic. So how's the electron movement going to be from there?
The
Huh?
The bottom double bond attacks. I don't know.
Well,
I have a question. So when do you use like half arrows and stuff?
oh, these are all full arrows. You mean like this?
Yeah.
You only use that if it's a radical. Some of these I just suck at drawing. They're all supposed to be full arrows.
Okay.
So Diels, you were really, really, really close, right? So you said that you start with this one.
Yeah, that one.
So now it could either go here or here, right?
To the bottom.
You're saying the bottom.
Yes.
Does anyone have any disagreements with that? Yes, no, maybe so.
I mean, that's what gets attacked, so it has to be the bottom.
Yeah, it has to be the bottom.
Mm-hmm.
And then what does that mean about the other part?
So the double bond of the electrophile goes to the top carbon?
Saying like this?
Yes.
Yes. And there's one more step, right? Or one more movement.
So the pi bond of that top carbon goes. Yeah.
Yeah, it just goes down on.
Yeah.
And so in our product, we're going to form a cyclo ring, so a cyclohexene, or hex, yeah, it's a hexene. So the hard part, I honestly think that the hardest part is figuring out the stereochemistry. So when I draw these in, these guys become chiral carbons, don't they? So Moses says yes.
Usually, yeah.
Yeah. So what do you guys think?
Yeah.
So yeah, they become chiral carbons. So this kind of goes back to the definition of chirality. Why do they gain chirality?
Well, don't those carbons become sp3 hybridized at the end?
Mm-hmm. They do. So they become sp3 hybridized and well, Moses, I'll say, be quiet really quick. Sorry. I feel like Dr. Lee and I can be so rude. We're just like, Moses, be quiet. But anyways, but we always mean it in a good heart. So for everyone else, what's the other requirement for chirality?
I don't understand the question.
So do you remember chirality?
Yeah.
Yeah. So the thing is that these carbons right here and right here, they become chiral in the product. So the question is basically why. And Moses said that they gain sp3 hybridization, but then there's one other requirement that has to be there for chirality to be a thing.
They're not symmetrical?
I think that's one way to put it, yeah. I think there's another way that I would put it that's a little bit more specific.
Isn't it just having like 4 unique groups?
Yeah, exactly. It just needs 4 different groups. So I guess I've heard it called an asymmetric carbon, but it just means that it has 4 different groups. So, oh wait, I shouldn't have done that. So, so why does it matter if it's chiral?
Or like meso, I forgot the word. Meso or
What do you think, Sarah?
I don't know.
Yeah, no?
No.
So whenever we do mechanisms, the thing about the products that matters really is regiochemistry. So where do things end up? We covered that with the resonance and stuff. But then there's also stereochemistry, right? So if something is chiral, or if it's or if there's something around the double bond that's all funky and weird, I mean, we don't really have to worry about that all that much with these problems. Then it's going to have stereochemistry, right? And we have to think about what the stereochemistry is. Does that make sense? I think I got one nod from that.
So it has to do with enantiomers, right?
What was it?
It has to do with enantiomers?
It can. It doesn't always have to, but there are problems where you do get, I think you get enantiomers sometimes. It's not very common, but you're thinking around the right idea. It has to do with the orientation of these guys and the product, right? So the next question we have to ask is, are these up or are they down?
Oh.
I know it was a simple answer, but you guys need to be able to like think about that. Just say like, okay, well, this change is happening. So now I have to think about this extra thing. And it's a pretty big part of the Diels Alder reaction. So how are we going to figure out whether or not it's up or down?
Does this have to do with like a backside attack?
Not quite. So it's actually something that's very, very, very specific to the Diels Alder reaction.
Oh.
So
Wouldn't they both have to be either up or down?
they don't both have to be.
They don't?
Yeah, so there's kind of a technique that I learned back when I did this that helped out a lot, but it's a little hard to explain, especially over this. But there's a specific rule that Dr. Lee, well, I mean, I didn't see the lecture for this, but I assume he went over it, that Dr. Lee went over, called the Endo Rule, right?
Crap.
Mhm.
Yeah.
Yeah. So that's just another layer to this reaction. So what does the Endo Rule state?
The pi system being added must be oriented toward or conjugated to the existing system away from the bridge.
I'm guessing that's true. I'm not entirely sure because I think it's. Can you read that again?
Yeah, okay. Or here, another way, the pi bond within the diene mediates ways it can approach the dienophile.
That's true. So there's a certain quality about the dienophile. That I think. Do you guys mind if I erase these resonance structures over here?
Go for it.
Can I go for it?
Yeah.
All right. So, dang it.
So endo just means down?
It kind of means down. Well, yeah, actually, it does mean down to an extent. Yeah.
The only notes I have for it is that it's usually for bridge systems.
Yeah, it's usually most important for bridge systems. I think, dang, there's like a, there's like a rule for it that I've seen.
Oops.
Let's see if I could find something really quick. Actually, wait a second. So they both end up down. And this is actually a problem in the book. But okay, so I'm going to draw a picture for you guys. So we have to think kind of about how they are orientated or how they're approaching each other in 3D space. So, oh, wait a second. So what I'm trying to draw in this picture is I'm trying to say that this guy is on top and this guy's on bottom. What was that? And so the idea with this is that, so the Endo Rule basically states something along the lines of, it usually happens if the withdrawing group is conjugated, or not conjugated, but if it has this double bond here. So this double bond is a pi system, right? Or it has these two p orbitals in it. Does everyone agree? I'm getting a lot of blank stares. I'm a little worried, but
I agree.
okay.
Yeah.
So I have agreement. So there's p orbitals in this guy. And then the intermediate, while this transition is going on, also has p orbitals here. And so you have all of this electron movement going on. It's a little bit hard to see. But basically the idea is that these p orbitals have what's called a secondary overlap, where the p orbitals in this guy kind of overlap with the p orbitals in the system of, in the conjugated system of the diene, and then that allows the intermediate, or I'm sorry, not the intermediate, the transition state to be more stable. Does that kind of make sense?
Yes.
Mm-hmm. Yeah.
So in order for that to work, the p orbital has to be basically close. It has to be basically underneath it. So can you guys see me?
Yeah.
Yeah.
So the idea is basically, here's, give me a second. So here's my diene, and here's my dienophile, and then, I don't know, here's like nah, dang it, this is terrible. I'm sorry. I should have come up with a better explanation for this. But here's kind of my withdrawing group. Is that okay? So the idea is that the withdrawing group has to be able to overlap with the pi system that's going on right here. Right? Dang. No, I have a molecular orbital kit over there. I could probably use that next time. So in order for that to happen, it's going to approach in the position that's going to be more or less down beneath it. So that way the overlap occurs. So generally speaking, that affects whether or not it's going to be, whether or not the withdrawing group is going to be down in the product. Does that kind of help or no?
I mean, it makes sense,
Yeah.
but like, I don't know. I just need to do it more.
Yeah, I think maybe in the next session I could pull up a kit or something like that.
Yeah, he explained this during lab, if you guys remember.
Yeah.
Yeah.
How it always had to be
30 minutes on it.
Yeah, I remember he spent a really long time on this section.
Yeah.
Well,
because it's
just the orbitals, like he kept pulling them out and just kept messing with them.
Yeah.
So I know this is a terribly drawn picture. But basically, oftentimes, I guess I'll just state this as a general rule. Oftentimes, the withdrawing group is going to be down if it has double bonds in it. That's just kind of a general rule. It's not exact, but it's approximate.
Only double bonds?
Well, it may be triple bonds, but generally speaking, like most of the withdrawing groups are going to look kind of like this, or it's going to be something like this. So unless it's basically like you'll see when you do the problems and the homework and stuff like that, most of the withdrawing groups are either acids, ketones, aldehydes, or cyano groups, or just not there. So yeah, that's the best explanation I could really do. I'm not gonna spend too much more time on it. But was that kind of helpful for that?
Mm-hmm. Yeah.
So that kind of explains why the withdrawing group itself goes down. But then the hard part kind of is just knowing that this guy goes down. And what it's a little hard to explain without being in person. So I'm just going to say that generally speaking, wait a second. If you have something like this, and you just have some substituent, generally speaking, this is going to end up down. And generally speaking, something like this is going to end up up. And there's a visual example, like way of explaining it that I came up with, but I just don't know how to explain it over the internet, so I'm not going to try. But if someone wants to come to my tutoring on Friday, I could definitely give it a go. But then you guys have lab, so anyways. So are you guys good to move on? Huh?
You're having tutoring on Friday? Where at?
Well, it's online, so you have to go to the Narco College website and then kind of navigate that. So there's a whole bunch of other stuff that I kind of want to talk about, but we covered most of it for that. Spent much more time than I wanted to, but that I feel like that's just kind of the nature of this kind of material. So are we all good? Is everyone? Yeah. Does anyone have any questions, or is anyone just like, what the heck just happened?
Take practice.
Yeah, but it takes practice. Again, I have the solution manual, so when you do these problems online, please, if you have a question, just ask me and I'll send you a picture of it. Because you won't do it right unless you know that you're doing it right. So do you guys mind if I erase this?
No.
All right. So I'm gonna draw some examples. Oh, this is 1530, by the way, from the book. So again, this is just predict the products. Oh, dang it. I always do that. The cool thing about the Diels Alder reaction is that you also get some really ugly looking products, and it's kind of fun to learn how to draw them.
Mhm.
And I know that it's kind of awkward to do over this format, but if you guys can work together, please do. Once I learn a little bit more about how to use Zoom, I'm going to be able to do something called breakout rooms, which is basically when I have like a timed section where you guys go into like little groups and you can only talk to each other for like 5 to 10 minutes. So I'll probably do that in the future, so that way you guys have to talk to each other. Oh, I completely didn't draw what that was.
Where's the bird noise coming from?
It sounds cute.
I think that might be me.
It's cute.
So this last one I'm going to change up a little bit. Ugh. Oh man. So these are just predicted product, by the way. Oh, I'll give you guys about 3 more minutes, and then how many of you have made good progress on A? I think 3 of you, 2 of you. So I'll let you guys finish up the problem that you're on, and then we'll start going through A. All right. So, are you guys ready for A?
Yeah.
So, I guess, well, really quickly, so what kind of shape does it make? I guess what's the general shape? That was a really dumb question, actually.
A ring?
So it makes a ring. What kind of ring?
Cyclohexene?
So it makes a cyclohexene. So what I'm going to do is I'm going to draw a cyclohexene, and then bond goes here. Pretty much every Diels Alder reaction has a bond going there. And then I'll have you guys tell me between 1, 2, 3, 4, what goes on it. What goes on 1?
Nothing.
Yeah. So nothing goes on 1. What about 2?
Nothing.
Nothing. What about 3?
Something.
The
Something.
withdrawing group. Yeah.
Yeah. So the withdrawing group goes there, right?
Yeah.
Yeah.
So what can we say about the withdrawing group? Oh, and then 4 is nothing, right?
Yeah.
Mhm.
So what about the withdrawing group? It's
The
there.
Endo Rule.
So the Endo Rule is true. There's something that, so you're saying that it would, so how would it show up? Like up, down, or just racemic?
I want to say down.
You want to say down. What do you guys think?
Mm,
Racemic.
So I have 1 down, 1 racemic.
Racemic, I think.
How would you know if it's racemic?
Well, we'll talk about that.
Okay.
So Sarah and Maddie, what do you guys say?
I don't know, but I'm just I don't know.
What did you put?
I understand what I mean I don't know, never mind. I don't know.
So give an argument for why it would be down. If you think, if anyone thinks it's down.
mm,
No one's giving an argument. That makes me sad.
Oh, 1.
Would you have to write plus an enantiomer because it's not miso?
I think you can actually. So you could say,
Mhm.
and that should be the same thing as racemic, right?
Yeah.
Yeah.
So I take it back.
Yeah. So you're taking it back, and
Oh, okay, I see now.
yeah.
That makes sense.
So does anyone want to give a reason why it's not up or down? It's both.
I mean, wouldn't it be because on your dyeing you don't have any substituents on it, nor are you making a bridge compound in your product?
Pretty much. Yeah, that's pretty much what it is. It's just saying that there's nothing else to really compare it to. I guess there's nothing else that could be up or down relative to. So you're just going to get one product. And there's no preference for that product. So basically, like if we're thinking of it with the Endo Rule, it could either attack this way or it could attack this way. It doesn't have a preference. And it doesn't really matter where that substituent goes because, even if it is stabilizing it with the Endo Rule, there's nothing else for it to be up or down compared to. Does that kind of make sense?
oh yeah, that makes sense.
Yeah. So either way, if it's up, it's also down because you could just flip the molecule. So yeah. So that one I think is actually a little bit tricky because of that. So what about B? Did anyone get B?
So that's where my issue starts. I'm not 100% on mechanisms when it comes to triple bonds.
So it's pretty much the exact same thing. That's the thing.
Okay.
So if it's, regardless of if it's a triple bond or a double bond, the only thing that changes is basically whether or not one of the carbons is electrophilic. And even then, it's probably going to be the same one as compared to if it were a double bond.
Yeah.
So I guess what kind of ring do we have?
One, two, three.
Kind of ring.
in the product.
Cyclohexadiene?
Yeah.
Yeah, it's a cyclohexadiene. Diene, not dying, like us. I'm just kidding. We're not dying. We're surviving. We're getting through the, what should we call it, the disease. So it's going to be a cyclohexadiene, which just means that it has two alkene groups, or two double bonds. So what about the withdrawing group?
You mean where does it go?
Yeah, what about the withdrawing group?
Yeah, when does it withdraw?
I mean,
Does it withdraw?
What was the question?
Well, so where does the withdrawing group end up? And it does withdraw, but I guess the question is, does it really matter all that much?
No.
No, it doesn't really matter all that much. Why doesn't it matter?
It could go either way. It's the same thing.
Yeah, it can either go here or here. But there is something else. There is something that does make the stereochemistry matter. So regiochemically, it doesn't matter because there's not really there. It's like this diene is symmetrical, and then this dienophile only has one group on it, so it doesn't really matter. It could. So let's just draw it here arbitrarily. But then stereochemically, there's something about this molecule that we're actually missing that makes the stereochemistry not racemic.
isn't it the bridged compound?
Yeah, so it's a bridge compound, right? What does bridged mean?
It has a bridge.
Yeah, so it has a bridge. So where's the bridge going to start? I guess, is it going to start on any of these guys?
No.
No.
It's going to start on one of these, right?
Mhm.
Oh, hey, I made it a sun. So that's really bad. There we go. Does everyone kind of understand what's going on here? So there's a carbon here and a carbon here. And so basically it's just saying that there's a cyclohexane here and then a bridge going across it. So I guess a better way to draw it is like this, right?
Yeah.
So that's the same thing as this. So the question is the withdrawing group up or down? Or actually, does it matter? Sorry, that was a really different question. Does it matter?
It doesn't?
It doesn't matter.
Yes, sp2 hybridized, so one is the planar to
Yeah,
the rest of the compound.
Exactly. That's actually something I have in my notes for this one, but I forgot to write it. Or I forgot to mention it. Does that one make sense to everyone?
How do you know when a bridge actually happens?
So this is pretty much a rule for every Diels Alder reaction. If the dienophile is a ring,
Mm-hmm.
you get a bridge.
Okay.
So I'm going to label this 1 and 2. 1, 2. I did. You just patted me in front of everyone. So does that make sense?
Yeah.
Any questions?
No.
A lot better.
Did you say a lot but no?
Huh?
Did you say a lot but no?
No, I'm feeling a lot better.
Okay, yeah. Yeah, I mean, it's not really that bad after you practice it, but you have to practice it a lot. I mean, as you can see, we've already gone over by 28 minutes, so. But I don't really mind because this is fun, and there's not much else to do. I mean, it's fun to me. I'm not sure about you guys.
No. I wish.
It's not fun. Even being in the SI session isn't fun. Oh, my heart.
It's not the SI session. It's just
I-
OChem is hard.
Yeah.
It is
It's
hard.
not fun at all.
Yeah, this class is a lot harder than 12A.
It's really weird. Like, there's a lot of weird things in this class.
Mm-hmm. All right. So let's do C. So I guess what kind of ring do we have?
A cyclohexene.
So it's a cyclohexene. Bridged, unbridged.
This should be bridged.
Yeah.
But
Yeah, so it's the unabridged version. So yeah, figuring out the general shape is the easiest part. That's what you should always do first. I don't even know if there's a time when it's not a cyclohexene, except for in like rare circumstances where it's like, oh, hey, it doesn't form a cyclohexene. It does this instead. Explain why, kind of thing. So, so now we have to figure out what.
Where the withdrawing group would go?
Mm-hmm. So where does it go?
would it matter in this case too?
What do you guys think?
I don't think it matters.
Yeah, so where it goes does not matter, but there is something else that does matter. So let's just say that it attaches here. So what's the other thing that matters?
Stereochemistry.
Yeah.
Yeah, so what's the question with stereochemistry?
Up or down?
Up, down, or racemic, right? So is it racemic?
Yes, I think.
What do you guys think?
Yeah, I'm gonna go with yes.
So Diels is saying yes.
No.
Would the bridge make a difference?
Well, what do you guys think?
Sure, it makes a difference.
So you're saying sure, it makes a difference.
Yeah.
It would be stereospecific.
But they wouldn't have made a difference in the previous question?
In the previous question, so there's the reason why it doesn't in the previous question is because the carbon that substituent is attached to is what?
A double bond?
Yeah, it's double bond. So that means that it's planar, right?
Okay,
In
yeah,
this
yeah.
case, it's not a double bond, so it's not planar.
I see now.
So it's not racemic?
Yeah, well, it turns out that it's not racemic. So that means that we have to figure out whether or not it's up or down, right?
Right.
So what do we do? What do we do? What do we do?
Is this where the Endo Rule comes in?
What do you guys think?
Yes.
Yeah.
So yeah, it's where the Endo Rule comes in, right? So if we have the Endo Rule coming in, how is it going to change things?
It would have to be down.
It would have to be down relative to the bridge.
Yes.
Mm-hmm. So why is down endo instead of up?
Because it's always down. That's what endo means.
Well, it kind of depends. So remember when I said back whenever we have a group that's in like this, it's going to be up, and out like this, it's going to be down. You guys remember that?
Yes.
And that's relative to the drawing group, right?
Mm-hmm.
So it's pretty much because in the bridge system, both of these guys are going in. And so they're both going to be pushed up. So like the way I kind of think of it is that it's approaching it like this, and then when it comes in, it pushes that carbon upwards. And so you're going to have that group going down, but then the carbons in the bridge part are going to be going up. It's just
Okay.
how it is. Are we all good on that?
Yeah.
So would he want us to draw it either or is there a specific way? Like,
It doesn't matter. It's just whichever one you want. I think it's easier to see with where you have like the 3D version.
yeah,
Mhm.
that's how I draw.
Okay.
So let's do D. So what kind of ring?
Cyclohexane.
The answer is yes. And so now what do we have to figure out?
Stereochemistry.
So stereochemistry, but there's something else that we kind of want to do before that.
With drawing?
Yeah.
Group?
Yeah. So we want to analyze the withdrawing group and the substituent on the diene, right?
Mhm.
And how do we do that?
Resonance, like the example you showed us.
Mm-hmm. Oh, actually, this is the exact same one. So,
Yeah, it looks the exact same.
yeah, it's
Yeah.
the exact same one. So do you guys want to go through it at all or no?
Mm.
Mm.
Yeah.
No, we know. I don't know
Um,
about you guys.
Yeah, yeah, we'll be fine.
all right. So yeah, I mean, we already did that one. So I think that E and F are the harder ones.
Yeah, that's tricky.
We
Why are they hard?
Because the diene is trans.
Yeah. So the diene is what kind of trans?
Is it S trans?
Good. Does everyone else see the problem with it? Yeah. Okay. Cool.
Yeah.
So So we have to do what before we go on?
Make it cis?
We have to make it S-cis. So how do we do that?
That I don't know. I probably do. I'm just blanking.
You want to rotate it about the sigma bond in between the pi bonds?
Oh.
Right. Oh wait. Yeah. So Moses is right. Whenever you see this S-cis thing and it's doing a Diels Alder reaction, S-trans, it means that you have to rotate this guy, and it's kind of tricky to do. But so we rotate around that. We want to rotate it 180 degrees. So I guess if we rotate it, we know that's going to look kind of like this, right? But then what's the question that we have to figure out before we add on our substituents?
Whether they go up or down?
Not quite up or down. Well, I guess up or down, kind of. Up or down in the drawing, but. What do you guys think? I feel like you just threatened me, Maddie. You were like.
I don't know.
I actually look kind of weird, like. I don't know. Anyways.
I mean,
So, Diala, what did you mean by up or down?
Is he coming back? Oh, there he is.
I have no idea what happened.
I don't know. Also, your cam froze while you were eating, and then you disappeared.
So you just saw a shot of me going like, I'm just kidding. Ah, dang it. Everything disappeared. No.
Back on the one we're working on.
We have them down, so it's fine.
Down.
Yeah.
Well, I also sent these over to you over email. I think I'm going to be doing that. I'll just send them to like the day before or something like that. So you guys can like look at them or think about it. Because I feel like the material is going to be too hard to do everything on like within the session from here on out.
Yeah, makes sense.
You guys should be able to think about it beforehand. Dr. Lee's giving the quiz next week, right?
Yeah.
I think it's Thursday.
As in tomorrow?
Wasn't
No.
it next Thursday?
No, next.
Yeah, next week.
Okay, cool.
If it was tomorrow, I would not do well at all.
No, we're not gonna finish chapter 16. Well, no.
Mhm.
I think chapter
Wait,
15. Huh?
Is our quiz on just 15 or is it 15 and 16?
I think it's just 15.
Yeah.
Maybe. I'm not sure.
I'm gonna ask him tomorrow.
Since we don't actually do labs, is he actually going to make us sit there for about 6 hours?
That's what I was wondering too.
Lecturing?
I don't think we will.
Well, he's in a lecture.
Yeah.
The rest of chapter 16, the
I
start
would
is
think like 3 hours at most.
And
I
he said
mean-
he wants to do 17 too, so
yeah.
Oh, I forgot
it'll
about
be a
that.
very long day.
I
Yeah.
think he's only going to do that until he catches up. Because we're like 4 lectures behind.
Yeah.
Yeah.
Oh my god.
Because last year I would have had my exam last week.
Oh.
I remember because there was a wedding that day, and I got a notification for it on Facebook, or like the anniversary or something like that. They were like, "Oh, I love you so much," to each other, not to me. But I was like, "Oh yeah."
So how would you solve this?
So we rotate it around that, right? Does everyone kind of understand that?
Mm-hmm.
Maddie, you look sad.
I am. I'm stressed. Like I just want to study for the quiz. Like, I just don't know what this man is gonna give us. You never know.
So the hard part with this is, oh, I drew the last one.
Yeah.
I guess we could do them side by side. So we rotate both of them 180 degrees around this bond. So the thing that's hard about this, we know that it's going to end up being this shape, because that's the goal, right? Is to make it that shape.
Mm-hmm.
But the question is it going to be like this,
No, man.
or like this, or like this? So it's, I don't know how to really show it, but basically this guy's still going to be sticking out. This guy's still sticking out. But this guy goes from here to here. So I kind of flipped it around. But basically it's boom, 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 boom. So this guy comes over here, and so it looks like that.
Mm.
Does that make sense to everyone?
Okay.
It's really hard to show. I would recommend, actually, I'm too lazy to do that.
The kit.
Yeah, I could do it tomorrow, because we're going to have an essay session tomorrow.
I get it.
So product is going to be, of course, it's cyclohexene. So the question is basically, what's the stereochemistry, right? So how do we do that?
Since the cyanide is cis, both of them, would they both have to be up together or down together?
Mm-hmm. That's true. So do you guys, so we could just draw that. We could say, okay, well, it's up or down. Now we just have to figure out whether or not the methyls are also up or down. So let's just draw these down. Because it doesn't really matter as long as we're consistent.
Mhm.
Oh, dang it.
Is this the case where if something is coming from the bottom, it pushes other stuff up?
Yeah, so I'm trying to come up with an illustration for that right here. Do you guys want to see what I kind of come up with?
Mhm.
So again, everything is kind of beneath that. So up, down. Here's our dienophile, and here's our diene. So the way I think of it is, as this approaches, so it's going to kind of do this mechanism thing. But as it gets closer and closer together, everything is going to be pushed up so that these guys are going to be down for sure. But then the way I think of it is I think of this as a lever arm. Does that kind of make sense? I think of it as like a lever arm that's attached to this carbon and this carbon. And so when it comes in, it's going to push this lever arm up. And that's going to push these guys down. I'm not sure if that makes any sense at all. But it's the way I thought of it, and I thought it was very helpful.
Could you like show that again, the lever arm part?
Yeah. So I'll do it in a different color.
Yeah, can you do different colors?
Yeah. It's like super ugly. I don't like doing different colors for some reason. It's just like a thing. So I'm going to get rid of the arrows for right now. Yeah, dang it. So as these guys approach, they're going to approach one another until they become on the same level. As that happens, because of the Endo Rule, we know that these guys are going to go down because these are cyanides. They have these p orbitals, so they follow the Endo Rule. And so these guys are going to end up down. But then as they approach, the way I think of it is I think of this as a lever arm right here. One attached to this carbon, one attached to this carbon. And so when they approach, I think of kind of like the force of them approaching and coming on the same plane as a force pushing on it like this.
Okay.
And then that causes this to rotate as it becomes a sigma bond until this goes down. And even though it's not really something that I found online, I just like thought of it and I was like, oh, that makes sense. It seems like a pretty consistent tendency that I've seen with Diels Alder reactions. And then, so if we were to replace oh no. If we put a CH3 here, then the CH3 becomes a lever arm, and the lever arm goes down, but the CH3 goes up. Does that actually help at all?
It does.
It does? Okay.
Mhm.
Cool.
Okay, yeah. Yeah.
Good.
All right. So, so with that in mind, up or down for these guys?
Mhm.
You said up?
Up.
Yeah.
should be down.
So Moses says down and everyone else says up. So I guess looking back at this, we're pushing up on the lever arm. So the lever arm is gonna, oh dang it. So the lever arm is gonna come up like this until it's in an up position.
Mm-hmm.
And these guys are gonna come down.
Mm-hmm.
The reds are the CH3s. Did I just confuse everyone? Or did that clarify it?
So the CH3s are down,
Yeah, so they're down.
but if they were pointing inwards, then they'd be up.
Yeah. So that's
Oh.
kind of a general thing.
So the CH3s were on the outside.
Yeah. But if the CH3s were inward like this, then it would be pushed.
Then it would be up.
Yeah.
Yeah. Okay, thank you.
Mm-hmm.
So they're all down.
So I'm going to just give you the answer for the last one. And then tomorrow, I think tomorrow I'll go over the big cool question that I wanted to go over today. I mean, we're an hour over. Almost an hour over. So I'll just give you the answer to the next one. Wait. Okay. So the last one is really quite tricky, I think. For F. So did the lever arm thing actually help everyone?
Yeah, it helped me.
So it didn't help Alex though. Okay. So I guess in general, so if you don't want to look at the lever arm thing might be super confusing. Just think that if it's out, usually it's going to go down, and if it's in, usually it's going to go up.
Wait, say that again? Sorry.
So if it's out, it's going to be down. If it's in, it's usually going to be up in the product. And the lever arm thing is just kind of how I thought of it. It's not like a rule. It's not written anywhere. It's just kind of how I was able to rationalize why that is.
Okay.
Am I good? I'll erase the lever arm thing.
Hey, I gotta go, but I'll be back tomorrow. All right.
Okay.
All right. Thank you so much.
Yeah, of course.
So in this case, it would be one cyanide out and the other in or down.
Oh, yeah. Sorry, the way I have it in my thing is different. So the problem with this, let me see here. Wait a second. And then same thing with these. One of these is going to be up and one is going to be down.
Mhm.
Does it have to be respective to the CN?
No. So in reality, and in the actual question, the CNs were both like this. And I just made the switch over there to make the point that one is going to be up and one is going to be down. But I think that you're going to get a mixture of products where it's something like this. I think you're going to get a mixture, but I'm not certain.
I know that like when he went over something like this in lab, like he was able to say like what percentage would be higher or like which one would be higher. Like how would you know? Or was that for a different thing?
I don't think he would expect you guys to know that. I'm guessing that there's probably some sort of a stability in the product that has to do with like the chair-like conformation of this guy. But the chair conformations for these alkene groups are not just like the typical weird looking.
Interesting.
Is that a bat?
A dragon? Yeah.
I thought because of like the virus and everything.
It's fire. Okay. Anyways, so that last one, yeah, that last one is a little bit iffy. I'm pretty sure it's a mixture, but if it is, then you won't really be able to just say, oh, hey, this one's higher than this one. You're just going to get a mixture. So, all right, well, I think that's pretty much it. I went over because I really wanted to make sure that you guys went over all of this stuff. This is a pretty hard section. I think that chapters 15 and 16 are the coolest in the entire book because it's the most like theoretical. And it's kind of cool. I don't know. I think that aromaticity is really awesome. But the mechanisms for in chapter 17 are really annoying because they're not hard, they're just different. And it's just not fun. But like chapter 16 was really cool. So
What's like the worst chapter?
I think chapters 17 through 19. I think chapter 19 was my least favorite. Chapter 18 was probably the hardest. And chapter 17 was just the most annoying.
It is.
Yeah. Well, you haven't even gotten to chapter 17.
Moses reads the whole book before lecture.
I'm kind of like halfway through 17, and I get it, but I'm not liking it though.
Yeah.
What is it about?
It's the same thing for me. Like I studied for the exam, or no, I studied for the quiz. I got a good grade on the quiz, and then I came to the exam and I completely forgot everything because there's no like logic that you could really follow that's normal with the rest of the class. Like there's a logic to that chapter specifically, but it changes everything. And it's just really annoying. It's so different. But
and it's just what is it? It's just reactions involving aromatic compounds is what it is.
yeah, it's just breaking those rings or breaking up the aromatic system.
Great.
Can't wait.
You can wait.
So,
Oh, Maddie left. I didn't notice that. Dang.
Yeah, she said her cats were fighting.
Oh.
I would just let one of the cats die because organic chemistry is so cool, you know?
No.
Kidding.
Alex, what are you eating?
It's Mediterranean food, but it's like white people Mediterranean food. So it's like
Wait,
French
like
fries.
Eastern?
There's like French fries and lamb or something like that.
Americanized Mediterranean, essentially.
Yeah, but like actual Mediterranean food is so much better than Americanized Mediterranean food. So
True.
Across all cultures.
Where is it from? Is it homemade?
no, I don't know where it's from. My parents were just like, "Oh, hey, we're gonna get food from this place, so I'm gonna get you something. I'm not gonna tell you what it is."
Huh.
But I mean, it's not bad. It's just kind of weird. It's a lot of fat.
Interesting.
So how are you guys adjusting to the whole online thing?
I hate it, but yeah.
I'm glad this is my only class, so I can't really say much, but it is a little weird, the online switch.
Mm-hmm.
Fun.
This is like the worst way to do this class. I think this is the hardest class in college. Maybe 4B. I think 4B might be harder, but
You know, I'm not even worried about physics 4B. I'm
okay.
more worried.
4B is definitely not harder if you're taking it with Russell.
Yeah, Russell's. Yeah, no.
Yeah. No, yeah. Apparently, wait. Do you know Harsha?
Yeah.
Were you there when she was getting into arguments with him about the Rocket Club?
I wasn't there, but I heard about it.
I don't know.
He's so
Like-
dramatic.
I know. Like, but then like afterwards, he was like, "Sorry, I might have gotten a little bit heated there," or something like that. But
I don't know why. He's just jealous because RCC can't compete.
it's true. Although the Rocket competition was canceled, so
Rip.
yeah, we saw it. But we're still gonna be training up for next year, so
That's good. But yeah, that's good. So is he invited or is he uninvited?
I have no idea. I think we like invited him and uninvited him 3 times or something like that.
Oh my gosh.
But yeah, he's weird because sometimes he just comes across as really irritated, and then he comes across as super nice, which is weird.
Yeah, I don't know. He has like a weird personality. I don't know. Like you think that he's I don't know, it's weird.
But then I heard that he likes Maddie because Maddie likes cats.
Okay, I'm gonna go. But yeah, he likes Maddie because she has a cat. I don't know why he likes me. I guess it's because I talk to him. But, yeah. All right, guys. I will
Alright.
see you
I
tomorrow.
have to go. Later.
Bye.
Be safe.
Thank you.
You too.
Oh, how do I leave this?